So I want to tell you, so yeah, thanks for the invitation and a chance to proselytize about things I like. So I want to introduce you to partitions. This is an area of mathematics which has, which is quite, now more than a century, well, it's many centuries old, but its effects are still being felt, and it's fairly elementary in the sense that you don't need much background to understand. So we will, so this is the topic of partitions. So we'll go slowly. We have two lectures. So we'll go slowly and we'll build towards some interesting mathematics. Okay. So I'll start. So I'm going to use the board only. So please tell me if my handwriting becomes too small or too low or anything like that. Let me try to divide the board up. See, I'll try it. Well, okay. It's probably not roughly equally for areas, but it should work. So, okay. So, is this height? Is this font visible? Font size 12 or whatever. Is it visible to you at the back? Yeah. Okay. So what we are going to, so all of you are familiar with primes, I suppose. You must have studied primes in your courses, and you must have studied various results about primes. Primes are of course very important and essential to mathematics, but there is an additive analog of primes. So primes have to do with multiplication, right? How you decompose a number into its multiplicative factors. We will do the analogous thing for addition, okay? In some sense that will sound easy, but then we'll build towards, we'll make things more interesting later on. Okay, so the first thing I want to define is a composition. So this is not function composition, this is composition as it is. A composition of a positive integer n is a tuple of integers, tuple of positive integers which sum to n. Okay, so I have an integer, let's say 5. I construct all possible tuples of positive integers which sum to 5. Okay. So we'll go to examples immediately, but I want to give the definition of partitions and we'll compare the two. Okay. So this is the first definition. Second definition, a partition. So partition means several things in several contexts. For us, throughout, partition will be referring to integers only, not partitions of sets. You may have seen partitions of sets in other areas of mathematics. That's also, I mean, it means more or less the same thing, but here we are only talking about integers. So a partition of an integer n is a weakly decreasing sequence of positive integers which sum to n. Okay, so the two definitions look very similar, right? But they are different, and let's do some examples. So let's take n equals 3. Okay, that's easy enough. Okay, so is everything clear in this? Does everybody understand what weakly decreasing means? Weakly decreasing might mean strictly decreasing or weakly decreasing, but just to be clear, we allow equality. Okay. So can someone volunteer to give me an example of, so here we'll do compositions here and partitions here. Okay, so someone can give me an example of a composition of 3, anybody? Sorry? 1,2, thank you. So that's one composition, right? So it's a tuple of numbers, and what is the property? Sum to 3, and they are all strictly positive. We don't allow zeros. Okay. Any other composition? Sorry? 1, 1, 1. Huh? Sorry? 5, 5. No, compositions of 3 of n equal to 3. 2, 1. Very good. So, these two are distinct. We don't think of these two as the same, right? These are tuples, not sets, right? And we allow repetition. So, 1, 1, 1 is really 1, 1, 1. It's not just one, a single one. Okay? Anything else? Good. 3 itself is a, right? I mean, that's a silly example, but it's still an example, right? We should not forget it, right? Anything else now? Okay, is everybody convinced that we have got all compositions of 3? Okay, all right. Partitions now. Can you give me a partition of 3? Sorry? 1, 2. Okay, so 1, 2 does not work because it's weakly decreasing. So as you read from left to right, the numbers should either be equal or decrease. Another way of saying weakly decreasing is non-increasing, but I don't like that because it suggests increasing, but I mean I want to say decreasing, but I allow for equality, so I say weakly decreasing. Okay? 2, 1, 1, 1, and 3, right? So everything here is also here, but this has extra stuff, right? So it's an easy observation that the number of, so observation, I won't even bother proving it because it's easy. Observation. What can you say about the number of compositions of n and the number of partitions of n? How are they related? Right. So number of, yeah, or you can say in terms of subset. Okay, let's say it this way. The collection of partitions of n is a subset or superset? Subset of the collection of compositions. Oh, my font size has become low. Is it still clear what I am writing? Guys at the back, is that okay? So composition, please tell me if it's not visible. Okay, is this okay? Okay, so I want to really spend most of the time on partitions because they are much more interesting family of objects, but let's first look at compositions, okay? So let Cn be the number of compositions of n, okay? So we want to count how many compositions are there of n, okay? I want to show you a way to count it, okay? So what we have seen so far says what? C3 is what? 4, right? So there are 4 compositions of 3. Okay, so now we'll do some mental arithmetic, okay? What is C1? 1, okay. What is C2? What are the 2 compositions of 2? 1, 1 and 2, good. Everybody is on board. C3, 4. Okay. Now let's check C4 and then we'll stop here. I don't have patience to do more than 4. Okay. So you just tell me, we'll start enumerating. 4 itself. Keep 2, 2, 3, 1, 1, 3. All ones. 1, 2, 1. 2 comma 1 comma 1 comma 1 comma 2, 2 comma 1. Ah, I counted that. Yeah. What else? Said. Four was the first thing we said. So we got everything. How many did we count? 8. Not 9, 8. We counted 8. Shall I repeat? 4. Okay, 4. I'll use fingers instead of that. 4, 3, 1, 1, 3, 2, 2. I'll not use the thumb. 2, 1, 1, 1, 2, 1, 1, 1, 2, and all ones. Agree? 8. Okay? Now do you see a pattern? 2 power n minus 1. So proposition C of n is 2 power n minus 1. Okay. So we have done enough examples. Can you think of a proof? It may help to write down compositions of 2 and 1 just to compare. We know what they are, but it may help to see how you might come up with a proof. Of 2, this is 2 and 1 comma 1. Compositions of 1 is just 1. So one way you can try to come up with a proof is to see how you can build compositions of 3 from compositions of 1 and 2. Can you see how to do that? There are many ways. Huh? Sorry? Induction, but for induction you need some idea which you will check. You need some formula that you can plug in and check. So how are you going to, right? So induction is a good strategy, right? But to induct you need to know the answer already. This is one of the drawbacks of an induction idea, right? You can verify an induction proof easily maybe, but you need to know the formula in advance, and we do know the formula, but we need to come up with some idea to be able to use induction, right? Yes? Yes? Or? Oh. Wonderful. Do you understand what he said? So any composition of n, right? In general now we are looking at n, is either just n, right? It was just 3 there, just 2 here. Or it's first there is a 1 and then the rest is a composition of n minus 1, right? Or you have 2 followed by a composition of n minus 2. And all such compositions will, and so on, I mean I didn't finish, but all the way up to n minus 1, right? And you have to think a little to convince yourself of 2 things. First of all, you get all compositions this way, number 1. And number 2, no 2 compositions from 2 different blocks are equal. This is a disjoint collection, right? Can you convince yourself of the disjointness? If I have a composition starting with 1 and a composition starting with 3, can they possibly be equal? No, because the first parts are different, right? So all of these will be distinct, right? And do you get all partitions this way? Yes, because every composition is either the trivial composition which is n, or it starts with something, and we have enumerated all possible things, right? So let us just check in this example. So for 3, it's either 3 itself, right, as you said. Okay, let me make a tick mark here. Or it starts with 1, in which case the remaining is either 2, maybe I'll use a colored chalk, is either 2 or 1 comma 1, and here are the 2 compositions of 2, right? or so this takes care of these two, or you start with 2 and then you have a composition of 1, and there is only one composition of 1, right? So that is this. Okay, is the idea clear? Everybody is okay with it? So the maybe I'll go here for the proof idea. I'll not go through all the details, but let us convince ourselves. So I didn't invent notation for the collection of all partitions. Let's call it of a composition, sorry. So let's say capital C of n be the collection of compositions. Can you see here? If I write here, can you see? Those of you here? Okay. So what the argument just made was that C of n is either n or it's, okay, I need some notation. I'll say how do I put it? So I want disjoint union here. C, let's say C 1 comma C, where C belongs to C of n minus 1, right? So here I am taking all compositions of n minus 1 and I'm putting a 1 before it, right? Union C in C of n minus 2, 2 comma C, etc. Union C in C of 1, n minus 1 comma C, right? This is what he said. I have just written it down in mathematics notation. Is this clear? Please feel free to ask questions. Any questions about this? I have just written down. So this notation is a bit maybe confusing. I just mean that you take the composition and you put a 1 in front of it. Okay? I mean, don't, there's some extra parentheses here if you like, but it should be clear what it means, right? This is exactly following this example idea. This will, okay, so then what will this imply for C of small c of n? What will this say for C, small c of n? Right, so small c of n is the cardinality of this, right? Size of this. That's the left hand side. What is the size of this? 1. What is the size of this? C n minus 1, right? Because we are taking exactly one composition from, we are counting 1 for each composition of size n minus 1, right? So this is C of n minus 1, similarly C of n minus 2, all the way up to C of 1, right? Because here I have C of 1, capital C of 1, right? Or a simpler way of writing it is sigma I equals 1 to n minus 1 C of I plus 1. Sorry. Yes? And now as he said, you can use induction, right? Once you have a formula like this, we have to give ourselves some initial condition. So because we are writing Cn in terms of all the smaller Ci's, so with initial condition C of 1 equal to 1, right? So once we have that, So once we have C of 1, then I can use this to get C of 2, and then I can use it again to get C of 3 and so on. Right? And now is it clear that this satisfies this? Has everybody seen geometric series? So when I put, so then the proof is just check this by induction. So proof. Check using induction. Right? Okay. Is this clear? Am I? Yeah, please feel free to ask. We can pause. What happens if I plug this formula here? Maybe I'll just erase. Okay. Let me just write here. So if I just plug it in here, I get C of n. I mean, check the base case. Then you get sigma I equals 1 to n minus 1. What is C of I? 2 power I minus 1 plus 1, right? What is this sum? Do you know this sum? What is that? You know the geometric series, right? I mean, I'm assuming everybody knows the geometric sum. What is 1 plus 2 plus up to 2 power n? That's a geometric series. What is the sum? Two minus 1 is 1. Right? Should we do it on the board, or is everybody comfortable? Do it? Shall I do it? Just tell me yes or no. Okay, no. So everybody knows this. Can I assume that you know this? 1 plus 2 plus 4 plus 8 etc. up to 2 to the n is 2 power n plus 1 minus 1. So when you do this, you will get, because there is an I minus 1, okay, maybe I'll do one more step. This is sigma I equals 0 to n minus 2, 2 to the I plus 1. I just shifted the index, right? And this is 2 to the n minus 1 plus 1. This sum is by the standard geometric series, 2 to the n plus n minus 1, and the 1s cancel and you get, right? Okay. So we proved it, we proved this formula, so it is correct, we have convinced ourselves. But this is a boring proof, I don't like this proof. I'll give you a better proof or more interesting proof. So you should, I mean, maybe you are not surprised, but the first time I saw this formula I was very surprised. Why should the number of compositions be a power of 2 exactly? Right? Isn't that strange? I mean, why? I mean, there should be some fundamental reason for it, no? So do you know something else that's counted by 2 power n? Power set, yes, thank you. Someone said that, power set, very good. That's exactly what I wanted to hear. So the power set of what is 2 to the n? The number of power set of what has cardinality 2 to the n minus 1? Set with n minus 1 elements, right? It's not 2 to the n, it's 2 to the n minus 1, right? So the number of subsets, okay, so now we'll forget about partitions for a while and let's look at subsets. So I'm going to look at subsets of 2, subsets of 1, 2. What are the subsets? Can you tell me? Huh? Empty set? singleton 1, singleton 2, 1 comma 2. So they have the same cardinality. Okay. So now what we are going to do is to find a bijective proof. We want to construct, so you're familiar with the notation 2 power n? Okay, so let me define that. So n for me is the collection 1 to n, okay, box n, okay, it's just the set 1 through n, it's just helpful to write. And 2 power n is the subsets, okay, power set of n, okay. Because I mean we write it this way because what is the cardinality of this power set? 2 power n. So we write it this way. So we just remove the brackets, you will get the cardinality. Okay. So we want a bijection f from C of n to what? 2 power box n minus 1. Okay. So I am going to build for you a bijection between these two sets. Okay. But let's see, let's try to build a bijection. I mean, what is the intuition? So we will actually prove something stronger. We will prove a statement about number of compositions with certain properties. We will show that it's equal to something else, some subcollection of this. So it will help to do this for n equals 4. I know it's a bit of work, but we'll do it. I mean, anyway, we counted it quickly. We'll just write it down quickly. And I want you to, I mean, here you might be able to spot it here, but it's much clearer for n equals 4. Okay, so we will do it. So can I erase this? All of you have taken this down? Okay. So I'll do n equals 4 and subsets of n minus 1, right? So n equals 4 now. Okay, so we already listed the composition, so I'll just do it. I'll not put parentheses and comma and everything, okay? I'll just write it because it'll be a pain to write everything in detail, but you understand what I'm talking about. So 4, 3, 1, 1, 3, 2, 2, 2, 1, 1, 1, 2, 1, 1, 1, 2, 1, 1, 1, 1, right? I've just listed everything that we talked about earlier, right? You see all the 8 compositions of 4. And what are the subsets of 1, 2, 3? 5, singleton 1. Okay, again I will not write all the curly braces and all that, it's a pain. 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3. Okay, just can you see some pattern, some quantity on the left counting something which is equal to some other quantity on the right counting something else? Can you match statistics? Can you just from observation? Wonderful. Very good. So did you hear what she said? So she's saying that it's somehow natural to take the singleton here, singleton composition mapping to the empty set. So if the composition has size 1, it maps to the empty set. There are 3 compositions with size 2 with 2 parts, and there are 3 subsets with 1 part. There are also 3 compositions with 3 parts, and there are 3 subsets with 2 parts, and there's 1 composition with 4 parts, and there is 1 subset with 3 parts. And does it, yes? Were you going to say something? Okay. So so this is 1. There's one element here. There are 3 elements here. There are 3 elements here. There's 1 element here. Do these numbers 1, 3, 3, 1 remind you of something? Anybody else? Pascal's triangle, right? So here also 1, 3, 3 and 1. And if I erase the size 3, but if you look at your notes and you compare, you should get 1, 2, 1, which is the Pascal's triangle of one size lower, of one row lower, right? You remember Pascal's triangle. It goes 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, right? 1, 4, 6, 4, 1, right? So, if this idea is correct, if our idea is correct, we should be able to find a bijection which not only gives us a map from, not only relates compositions to subsets, but it relates compositions with k parts to subsets of size k minus 1, right? So it's more information, and we know how many there are. How many subsets are there of of 1 through n minus 1 with k parts? N minus 1 choose k, right? The binomial coefficient, right? And we are going to therefore show that the number of compositions of n with let's say k parts is n minus 1 choose k minus 1. So we get more information. I am not only telling you how many compositions are there of a certain size, I am telling you how many compositions are there of a certain size with so many parts. I am giving you more information. So this bijection that we are going to construct will automatically give us a proof, right? This is the power of bijections. So when you have a bijective proof, you understand better why the counting is so nice. Okay, that's what I'm going to do. Okay, so let's do that. Let me leave this example here because we'll stare at it. Okay. So let me propose a bijection for you and we'll check that it is indeed a bijection, and I want you to think of the inverse map. Okay. Let me think, do I want to, which way should I? Okay, actually I would maybe prefer to do it the other way around. Two to the n minus 1 to c. Okay, so suppose the bijection. So suppose C, which I'll write as C1 up to Ck, belongs to C of n. Right? So it's a composition of n with how many parts? K parts, right? It's C1 through Ck. Oh, sorry, what am I doing? I wanted to do the other way. So I'll talk about subsets. Sorry. So S belonging to 2 to the n minus 1, I'll write capital S, and I'll write is written as S equal to, it's a subset, right? S1 up to Sk. So it's a subset of k parts. Sorry about that. As I said, I want a bijection which takes as input a subset and will return a composition. Okay, so then let f of s, now I am constructing a tuple, a composition. Okay. So first I will take just S1. Okay. So by the way, I should say that I am ordering this in increasing order. Okay. So S1, then S2 is bigger than S1 because it's a subset. So then there's only one with those elements. It's not a tuple, it's a set, right? So I can choose to order it any way I like. Okay, so I'm ordering it in increasing order. So I'll take S1, S2 minus S1. Okay, S2 minus S1 is also going to be a positive integer because these are all distinct, and it's in increasing order. S3 minus S2, etc. And then I will take Sk minus Sk minus 1. But you see, I want this should be a composition of, what should this be a composition of? Huh? K plus 1 parts. No, I understand, but what should be this be a composition of? Of what size? N. We want this to be a composition of n. But if I just sum all of these elements, what will I get? If I just close this here, I am in trouble. What is the sum of all these elements? Sk, right? Because S1 cancels here, S2 cancels here, S3 cancels here. At the end, I am only left with Sk. But I want a composition of n. Thank you. Perfect. So I'll tack on a n minus Sk. Okay. So then you see, how many parts does f of s have? K plus 1, as it should. Every subset of size k will correspond to a composition, subset of size k will correspond to a composition of size k plus 1. This is of size k plus 1, and it should be a composition of n. So it should sum to n, and now we have something that sums to n, and all the parts are positive integers, right, by construction, because S is an increasing collection. We have ordered the numbers in increasing way. So all of these are strictly positive. It's a set, so it cannot have any repeating elements, right? Is that clear? All the elements are distinct. We have arranged them in increasing order, and I am taking successive differences, and I have taken S1 also. Okay. So let us just check this idea. Okay. So we are unfortunately F will have to go from here to here. Okay, it's in the wrong direction, but you can think you are reading in Urdu instead of Hindi. So we'll go right to left. Yeah. Okay. So we'll tackle these cases later. These two cases we'll look at later because maybe that's a bit more complicated. What about the subset 1? So that's just S1, right? There's no S2. There's nothing here. So what will f of s be for that? 1 comma, which is? So where does it map to? Over here. Agree? Okay, now let's look at 2 comma 4 minus 2, which is 2, right? I mean, all of these will not be there. There is no S2, there is no S3, there is nothing else, right? So there is only n minus S1. So S1, n minus S1. So 2 will map to 2 comma 2, and 3 will map to 3 comma 1. Agreed? Okay. Let's look at 1, 2 now. 1, 2 will map to what? 1, then 2 minus 1, which is 1, and 2, 4 minus 2, right, which is 2. So this will map here. 1, 3 will map to what? 1, 2, 1. 1, 3 minus 1 which is 2 and 4 minus 3 which is 1. And 2 3 will map to 2 1 1. 2 3 minus 2 which is 1, 4 minus 3 which is 1. Okay, now let us do this base case. What if the subset is empty?
Just have n by less a, which is 4 minus 0,
4, exactly. So you have to interpret this correctly, right? So I mean, so then all of this is vacuous. There is nothing here, and there is only an n. Okay. So if you want, we will write where f of empty is n. That's a special case. And okay, this is easy. There's no problem here, right? Because 1, 2 minus 1, 3 minus 2, 4 minus 3. So, okay. So you see that this makes sense, right? It has at least for the n equals 4 given us a bijection. Okay. But how do you prove that this is a bijection? What is the strategy? Very good. So the standard way of proving that this is a bijection is to construct the inverse map. Okay. So let's construct the inverse. Let's think about how the inverse works. So we have all this data, right? So now suppose, can you sort of go backwards? Can you understand? So now suppose C is C1 up to Ck plus 1. Let's say k plus 1 because I want to build back something of a subset of size k. This in C of n. So how will you construct this subset? Let's look at some examples. So here what was happening, okay, let's just look at this part. So if I have this composition, what did I do to build this? No. So from 3 1 what did I get? What subset did I get? Which subset mapped to 3 1? 3. Which subset mapped to 2 2? Which subset mapped to 1 3? 1. So, just take the first element, right? In this case that worked. Okay, so that's simple. Now let's look here. 2 1 map to 2 3, 1 2 map to 1 3. Oh, sorry, 2 1 1 map to 2 3, 1 2 1 map to 1 3, 1 1 2 map to 1 2. So what is happening here? Very good. So here I take 2 and 2 plus 1, that gave me 3. Here 1 and 1 plus 2 gave me 1 3. Here 1 and 1 plus 1 gave me 1. But wait, something is wrong, right? I have forgotten the last element. Am I not losing information? Perfect. We already know that it's a composition of n. So if I remove the last element, I still know what that composition is. I am not losing any information. We know that this belong to the set of compositions of n, right? So even if I throw out the last element, there is no loss of information. So it's enough to build the subset from the first, in this case, k elements, because it's C1 through Ck plus 1. Okay? So what is the guess? So we claim that the inverse is what? Let's call it G. G of C is what is the first element? C1, second element C1 plus C2, etc. And last element up to Ck plus 1. No, is it Ck plus 1? Ck. Because C1, what is C1 plus up to Ck plus 1? No, it is n because it's a composition of n. So I can throw out that Ck plus 1. This is what I just said. Okay. So now to complete the proof, we have to show, what do we have to show? We have to show, right, exactly. F compose G of C equals C and G composed F of S equals S, right? And this, shall I leave you to check? It's not hard. So if I start with here, if I start with C, I get this. Now apply F to this. This is already in increasing order. So what would be, now just apply, so this is my S, okay. What is the first element of F of S? C1. What is the second element? No, S2 minus S1. What is S2 minus S1? Which is C2. What is S3 minus S2? C1 plus C2 plus C3 minus C1 plus C2, which is C3, etc. So you just do some checking. Okay, I'll leave that for you. But this is more or less the proof. Okay, so this I leave as an exercise, and basically this completes the proof, right? So here also we do the sanity check that this is a subset of n minus 1. Can you show that n will never occur here? N cannot occur, I mean, if it has to be a subset of n minus 1, each number has to be between 1 and n minus 1, right? We should never reach n. Can you show that? What do you mean? I mean, this is a composition of n, no? Right? But here we should not get n. We should only get numbers smaller than n. It's clear that these are increasing, right? Because all the entries are from are positive integers. So each time you are adding positive integers, so I just have to show that this guy is less than n. Can you show that?
Yes.
Why?
Because the sum of the whole sequence is n.
Precisely. The sum of everything is n, and we have removed something which is a positive integer. So this has to be less than n. Okay, so this does belong to the right, it does belong over here, 2 to the n minus 1. Okay, so that sanity check we have tested, and then you have to just verify this short calculation, and then we are done. So as a corollary, we have proved that the number of compositions of n with k parts, or if you like k plus 1 parts, let me be consistent, is n minus 1 choose k. You might be using different notation, n minus 1 ck some people write, but this is modern notation, n minus 1 with this big parenthesis. Okay. So it's a beautiful bijective proof because it gives more information. It's not only saying that from this bijection we get not only that the number of compositions of n is 2 power n minus 1, but number of compositions of n with k parts or k plus 1 parts is n minus 1 choose k, and then from this it follows immediately that the total number of compositions is 2 power n minus 1 because of the usual identity involving binomial coefficient, right? The sum of the entries in the Pascal's triangle at row n is 2 power n, right? So this will, right? So it's really elegant. Okay, everybody okay with this? Any questions? I'm going to change topics now. So are there any questions? Feel free to ask. If you want me to clarify any part of the bijection also, I'm happy to. Okay. All right. So let's move on now to partitions. Okay, so let me set some notation. So we will write we'll write a partition in Greek. Usually Greek letters are used for partitions. So we write lambda, which is lambda 1, lambda 2 up to lambda k, where lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda k is strictly greater than 0. Okay. So all of these are positive parts. So remember, for n equals 3, we have the partitions 3, 2, 1 and 1, 1, 1. Right? We wrote them down earlier, remember? So I will again not write parentheses, comma, all that, So please understand what. This is not 21 and 111 or anything. Right? It's 1, comma 1, comma 1. Okay? All right. Okay. So for later purposes, I think I want to work out, I want us to write down all the partitions of 6. Okay, there are not too many, we will just write them down systematically. So let's write all the partitions for n equals 6. Okay, so can you 6, 5 1, good, 4 3, 4 2, 4 1 1, very good, 3 3, good, you are writing it in order, very good, 3 2 1, yes, 3 1 1 1, 2 2 2 2, 2 2 1 1, 2 and 4 ones, all ones. Yeah, we have everything. I think you guys really did it systematically, so we have not omitted anything, right? So if the first partition, if the first part of the partition is k, then the remaining is a partition of n minus k, right? So once you put a 4 here, you get all the partitions of 2, and then once you put a 3 here, you get all partitions of 3, but once you put a 2 here, you don't get all partitions of 4, because it's already, you get only partitions of 4 which have first part at most 2, right? So then you get 2, these 3, and then all ones. Okay, so okay, very good. So we are there. Now I want to, so unlike compositions, partitions are not easy. There's no simple formula for partitions. Okay, so for number of compositions was 2 power n minus 1. Here it's much less, because remember we said that the set of partitions is a subset of the set of compositions. It is going to be much less, because for compositions we would have had 1 4 1 and 1 1 4, right? So we are omitting a lot. We are throwing away a lot of information, right? So the way to think about partitions, as I said at the beginning, is the additive analog of primes. Okay. So so what a partition is doing is telling you how an integer can be broken up into parts, broken up into pieces, and we don't care about the order of the pieces. So 4 1 1 or 4 plus 1 plus 1 is the same for us as 1 plus 4 plus 1, which is the same as 1 plus 1 plus 4. So just to keep everything straight in our heads, we just decide once and for all that we will write it in weakly decreasing order. We could have also done it in weakly increasing order, but someone has fixed the convention for us. I think Euler fixed it long time ago, and we just follow it, okay, to avoid confusion, right? We always write it in weakly decreasing order, so that there is only one representative of that sum, right? Okay. So now we want to count it. Okay. So to count it, I am going to make a detour. Okay. So this is a detour. So everybody knows the polynomial ring. Everybody has seen the polynomial ring in one variable, yeah? And you know what is the notation for the polynomial ring? Let's say with real coefficients, Rx, R adjoin x, right? So recall the polynomial ring. So this is the notation, right? R adjoin x. So these are polynomials in the variable x. X is some formal variable, right? So one thing it will be important for us from now on that we don't think of x as a real number. Okay? For polynomials, if I have f of x to be some polynomial 1 plus x squared or whatever, I can take x to be any real number, no problem, right? It will just give me some other real number. But what we are going to work with is something called formal power series. Okay? So let me just informally define it. So the formal power series, a formal power series is an expression of the form sigma an x power n. So it's just like a polynomial, except we allow infinitely many coefficients. Where an belongs to R. This is denoted R with 2 brackets x. Okay? So here it is now going to be very important that you don't set x to anything. If you are analytically minded, you might be worried about convergence. Okay? Don't. We are not thinking of convergence. X is not a real number. X is some variable. It's in the air. It's something. Hawa mein, you know. Katlar ke, whatever. I was trying to translate into Tamil. So you don't. So I'll give you an example. Okay. So let's say sigma 2 to the n x to the n. This is 1 plus 2x plus 4x squared plus etc. Right? So in your analysis course or something, you might have seen that this converges when mod x is less than 1 or some such thing, or whatever, less than half or whatever, I don't care. But we will not think that way. We are not going to assign any real number or complex number to x. X is just something. Okay, it's a variable. You're just not allowed to do that, right? So this is equal to 1 by 1 minus 2x, right? But here also we will think, so for us, this expression is equal to this expression. Equal, exactly equal. There is no conditional if, that, anything, okay, as a series. So this is an algebraic object, this is not an analytic object, okay. This is a ring itself, just like the polynomial ring is a ring, you can add, you can multiply, here also you can add, multiply, okay. There is an identity, there are inverses in certain cases. If you know about domains, if you know about integral domains, this is an example of an integral domain. In fact, it's a PID, you know, it has lots of properties, okay. Okay, is that clear? I mean, this is just some background, okay. So these are the objects that we are going to work with. Okay, so now okay, so given a sequence, so you know sequences, right? Again, from your analysis course, you know what sequences are. Again, we are not going to talk about convergence. So given a sequence an, I will always start with 0 because that will be convenient for me. The ordinary generating function will not always say ordinary, it will be understood, is the formal power series given by sigma an x bar. Okay. So if you are given any sequence, I can build this object, this function, or this kind of generalized function, if you like. Not really a function, because I have not told you anything about the domain or anything. And as I said repeatedly, we cannot assign x to anything, okay, but we can work with it, okay, and I will show you how. So for example, for the sequence an, if an is 2 power n, so I will call this by capital AX. So capital AX is 1 by 1 minus 2x, okay. So this generating function in this compact way encapsulates the entire sequence, right, because I can do Taylor series, right, or in this simple case it's a geometric series, but I can just expand and I just look at the coefficient of x power n, it will tell me an, right. So this simple function encapsulates this entire sequence. In some sense we have infinitely many pieces of information, right, A1, A2, A3, A4, etc. And in this AX everything is there, it has all of it, right. So it's a powerful idea and it's very useful. So in particular for many combinatorial sequences which count things, so if where an is counting something, then this turns out to be very useful. So in this case, again to repeat the example, if an is the cardinality, I'll just write it in words, of the power set of n of bracket n, then we know that that is 2 power n, we discussed it many times, then its generating function is 1 by 1 minus 2. Okay. I'll ask you to work out one example just to, or maybe we can work it out together. So let's work out one more interesting case. So you've all heard of the Fibonacci numbers? Okay, so good. So let's do the example of the Fibonacci. So this sounds stupid, right? You already know 2 power n. I mean, what's the big deal about writing it in this way, you know? But the Fibonacci numbers are much more interesting. So there's no really simple formula for the Fibonacci numbers, right? So there I'll show you how useful it is. Okay, so I don't know which way, there are many conventions for the Fibonacci numbers, but we will follow the following convention: f0 equal to 0, f1 equal to 1, and of course fn is fn minus 1 plus fn minus 2 for n greater than or equal to 2. Right, this is the standard recurrence for the Fibonacci numbers. Some people will start with 1 and 2, but this is more or less the almost canonical choice for various reasons, okay. So f2 is also 1, right, you see that, and then f3 is 2 and so on, okay. So let us compute the generating function for this, and I show you it's really simple, okay. So let fx, capital Fx, I usually take the convention that I write capital for the generating function and lowercase for the sequence. So sigma fn x bar. Okay. So I'll show you, or let's do it. So I want to use this recurrence, right? This thing star. I want to use this recurrence. But I cannot use it for f0 and f1, right? Because I can only use it starting with 2, right? But f0 and f1 I know what they are, right? So I'll write it in the following way: f0 x bar 0 plus f1 x bar 1 plus sigma n greater than or equal to 2, or let's say n equals 2 to infinity fn x bar, right? I have not done anything yet. I have just separated out the first two terms and I've written all the other terms together. Okay, I'm running out of space, so I'll move that here, equal to f0 is 0, so this goes away. f1 is 1 and x bar 1 is x, so this is x plus, right? And now sum n equals 2 to infinity. What is fn? Now I can use fn is fn minus 1 plus fn minus 2, right? Because n is greater than or equal to 2, right? So fn minus 1 plus fn minus 2 x bar n. Okay. Now can you see how to handle this term? Okay, again I am going to repeat. This is a formal power series, so I can split this into two sums. This is, I mean, in analysis this might be a problem, but for us it's not a problem. Okay. This is how in fact addition of two formal power series is defined, just coefficient wise addition. Okay. So I am going to split this sum. Okay, so it's x plus n equals to, I'll just write n greater than or equal to 2, fn minus 1 x to the n plus n greater than or equal to 2, fn minus 2 x bar. Right? Okay, I'll continue on this side. Oh, I should leave that example. We continue here. Can you see how to tackle the first term? Yes, what is, yes, someone said yes. What do you do?
We can take out x to the power 1 first sum and then x to the power 2 from second sum and get second.
So, yeah, can you say that again into the mic? So that
From the first one, we
will
take out x to the power 1.
Okay.
And from second one, we will take out x to the power 2.
Okay, so what he's saying is, I'll write x to the n as x to the n minus 1 times x. So I'll put an x minus 1, n minus 1 here and put an x here, right?
Yes.
Isn't that what you said? And for the second term, I'll put an x squared here and I'll put n minus 2 here. Why did you do that? Do you want to tell us?
Because then it's similar to the original equation.
Right.
So that will reduce it down.
So then these two match here and these two match here, right? And here these two matched. Okay, so that's why he did it this way, and that is basically he got the key idea. So let's write it. So f of x is x plus, now x times, this is n greater than or equal to 2. Okay, so so basically what is the first term here? f1 x bar 1, the next term is f2 x bar 2 and so on. Here what is the first term? f0 x bar 0, right? So the difference between this and this is just f0 x bar 0. Okay, so I'll just write it as f of x minus f0 x bar 0. You agree? This contains everything except the first term or the 0th term if you like, right? Similarly, where does this start? This starts f0 x bar 0. So this is exactly this. I don't even have to do anything, right? So the second, but remember that we pulled out an x squared times f of x. Okay? And now what is f0? 0. So actually it did not matter in this case. But in general, if I had some other initial condition, then it would matter, and it's better to be careful and do all the steps. Okay? So what we get is that f of x is x plus x f of x plus x squared f of x. So this whole recurrence for the Fibonacci numbers has given us a single algebraic equation for f of x. Can you solve it? Yeah, of course. It's there's no powers, right? It's linear in f. It's not linear in x, but it's linear in f of x. So if I take f of x common, I have 1 minus x squared here, and that is x. I took those terms on the other side. And so f of x is x by 1 minus x squared. Right? This is valid as a formal power series. And now, this is not a geometric series, right? It's much more complicated. So how do you solve this? So actually, you know how to solve it. Yeah, very good. Partial fractions. You know how to do partial fractions. Usually the kind of problems that you are asked will have these partial fractions will factor nicely. Here they don't factor nicely, but it's a quadratic, and you know what the roots of a quadratic, you know how to solve the quadratic equation. So I leave it as an exercise for you to do that. So, exercise. Okay. I think this is the answer, but please double check. So this will be 1 by root 5 x, 1 by x minus square root of 5 minus 1 by 2 minus 1 by x minus plus square root of 5 minus 1 by 2. This is x, this x is here, okay. So this is exercise. So okay, I'll put a small question mark here, just check the details. I may be missing a sign or something. And now you can expand these using, yeah, this is a geometric series, right. This is 1 by x minus something. So it's 1 plus x plus whatever. No, I think I've made a mistake here. I think it's 1 plus x. Sorry, I'm just trying to recall what the formula is. So then using this, you get that Fn is 1 by root 5 times square root of 5 plus 1 by 2 to the n minus square root of 5 minus 1 by 2. Again, there is a question mark here. Okay. So this gives a formula, a much more complicated formula for the Fibonacci numbers, right? It's not 2 power n or something. It's much more complicated. So this is called Binet's formula. Which you would probably not have seen. Okay. So using, so there is no trivial formula for this, but there is some formula that we can get. And in particular, this, do you know what this number is? Golden ratio. It's the golden ratio, and you might have seen that there is an intimate connection between the golden ratio and Fibonacci numbers. So in particular, if you take the ratio of successive Fibonacci numbers, the limit is going to be the golden ratio, and this you can see from here. Okay. So anyway, this is one of the ways in which generating functions are very, very useful. Okay. Okay. So all of this was a detour into generating functions, so that I can tell you about partitions. Okay. But I just wanted to tell you. So if you're not interested in partitions, all that, it's fine. But these generating functions are really powerful technique. They can be used in various settings. Sushmita, how much time do I have? 10 minutes. Okay. All right. So now let us come back to partitions. Okay. Can I erase this part of the board? You have all taken this down? Okay. So now I want to prove an amazing theorem due to Euler for the generating functions of the number of partitions. So the number of partitions I told you, just like Fibonacci, is not nice. There is no simple formula. but the generating function has an amazing formula. So this is the theorem. Let me first define. So let Pn be the number of partitions of n. So for example, what is P3? What is P3? 3. What is P6? 11, right? Over there. So this is the number. So here's the theorem due to Euler. Long time ago, I mean I'm not writing 1800 whatever. So the generating function n equals 0 to infinity Pn x power n. So we'll take P0 equal to 1, okay, by convention. So there's a silly way of saying this. So the number of partitions of 0 is 1 because there's only one way to do nothing. It's to build it by nothing. I mean, you just don't do anything. That's, you can do it only, you can do nothing in only one way. So P0 is 1. Okay, so I mean, and you'll see why that will make life very easy. So this is the product j equal to 1 to infinity 1 by 1 minus x power 0. That's it. So it's an infinite product. So far, both for the subsets and for the Fibonacci numbers, we had a simple rational function, right? But this is no longer a rational function because this is an infinite product, okay? Product 1 by 1 minus x power j, but j goes from 1 to infinity, okay? And here naturally you see the coefficient of x power 0 is 1. It will come up, it comes up naturally. So actually the hard part is finding this result, and this is where Euler was so good at these things. Once the proof is actually very easy. You just write it out. I'll show you in a second. But I want you to appreciate that even though Pn is very complicated, its generating function is very beautiful. Okay, and this has connections to other parts of mathematics. Like this is in number theory. This is an example of what's called a modular form, a very important object in number theory. Okay, so it's related to other things as well. Okay. So let me prove it for you actually. So it looks like it's such a huge result. I mean, how the hell could you prove it? It just uses geometric series, nothing else. So let's expand the right hand side. So that's all basically. Expand. So let's look at that. Let's just stare at the RHS for a bit. So what is the first term? Expand it. What's the first term? No, first expand the first factor. 1 plus x squared plus etc. times. So what's the second factor? Plus etc. times. Okay, we'll do one more. Plus x6 plus etc. Right? And so on, etc. Okay. Now let's look at a term. When you expand this, any term of the form x power n, I have infinitely many products, right? If it has x power n in it, that means from all but finitely many terms, we are only taking the one. Only in finitely many terms we are taking something else, right? If you take some other term in infinitely many terms, then you will get x power infinity or whatever. It makes no sense, right? So the only way you get a finite power is that you take one from infinitely many terms and take not one from only finitely many terms, right? Is that clear? That's the first part. Okay. So now you stare at, so how many ways can you get this x power n? That is the question. Okay. So let us just look at how you would get x power 1. So when I expand this out, again this expansion is in formal power series land. Okay. We are not allowed to set x to anything, right. So we are only comparing powers of x, that is the only thing we are allowed to do. And all we need to, the only thing that makes sense, or the only thing that we need to check is that any power of x makes sense, is of, I mean it's well defined, okay. So how can you get x power 1 from here? So look at x power 1. How can I get x power 1 in this expansion? Right. Is that what you were going to say? X from here and correct. That's what he also said. So to get x power 1, if I take x from here and 1 from everywhere else, then I get x power 1. This is one way, clearly, right? So, okay, so I don't know, I underline this. So, is there any other way I can get x power 1? You can talk into the mic.
We can take one from the, oh, it will be the same only. One from the, I was telling you, we can take one from the second factor.
One from the second.
And then again, but it will.
But we are going here one term by term, right? So, I mean, how do I build a term from a product, right? I take one from the first one from the second, one from the third, etc. Not one, like some term from the first, some from the second, some from the third, etc. Right? So this is one way. I take x from here and one from everywhere else. Is there any way, other way I can? A lot of you are shaking your heads. Can one of you justify? Yes?
Because if we take any other element
From,
let's say we are picking
Let's say we are picking anything other than x from the first one. So it will either be 1 or it will be some x to the power k.
yeah,
That k is greater than 1. So product will always give you something greater than 1.
correct.
Now if you have 1,
I
then,
take one.
Then whatever you will take from the other one, it will either be all of them will be 1. That will not never give you x to the power 1, or it will be x to the power k something, but x to the power k will never be, it will be greater than 1. So
Right? So everything is at least 2. Here the first term is x squared, here the first term is x cubed, etc. I think all of you intuitively realize this, and therefore you were nodding your heads. So there's only one way to get x power 1. Agreed? Everybody is okay with that statement? And how many partitions are there of 1? Only one. Not a coincidence. Okay. Now let's look at x squared. Okay, so maybe I'll write something. X to the 1, x from first, and 1 from rest. Okay? This is the only way. Now let's do x power 2. How can you get x squared? No, you answer everything, so I will not let you answer. Huh? Yes? 2 ways. First 2 from here.
First x squared from the first and 1 from the rest.
Yes? So
Or we
x
can-
squared from first and 1 from rest.
Or we can take x squared from the second and 1 from the rest.
Or x squared from second
And 1 from the rest.
and 1 from rest.
Yeah.
So that would be either this or this. Everybody agree? I cannot do anything else, because the moment I go beyond the third, I will get at least x cubed, right? Now, can you see that to get any x power n, I only need to look at certain number of terms. How many terms? First n terms, first n factors. Because anything after that will have at least x power n plus 1, right? So it's a finite computation. That's why it's a well defined as a product of formal power series. Okay? Now, okay, let's just to complete, and this will check with the x cubed. Let's look at x cubed. I mean, this will compare with partitions of size 3. Sushmita, I'll just take 2 minutes. Okay. X cubed, tell me. Volunteers. How can you get x cubed? No, you both have answered. I want someone else to answer. Yes. Sorry. Angayadu Kudumba. Speaking in Kannada.
So we can first take the x cube from the third.
Here?
Yeah.
Okay.
And multiply it with 1 all over.
Right. Just a second. X cubed from the third and 1 from the rest.
Or
Or?
x and x squared from the first two.
X from here and x squared from here.
Yeah.
Wonderful. X from first. No, x from first. X squared from second. And 1 from rest. Okay, whatever. You can't see beyond this, but it's 1 from the rest. Yes, what else? Is there anything else?
I can't see another one, yeah.
Well, okay. Look at the first term.
Oh, yeah. There's
This
an
is
x
an
cube.
infinite.
There's an x cube in the first. So
That's
x
right.
cube
So
there.
x cubed from first and 1 from rest. Anything else?
That's all.
That's all. So now you see the pattern. So to each term over here, we will be able to naturally associate a partition. And how? Does this give you a hint? So, yeah, okay, you see it. How about the others? So, this is the third, okay, so stare at this and this. So, I claim that the power of x here tells you how many ones there are. The power of x here tells you how many 2's there are. X squared means there is 1 2, not that there are 2 2's. Okay? So here when I had x cubed, the x cubed from here, that corresponded to having 3 1's. So this corresponds to number of 1's, this corresponds to number of 2's, number of 3's, and so on. So this term over here, the first one, corresponded to 1 1 1, what you just said, right? Because that, oh no, sorry, that corresponds to 3. Because I am taking the first non-trivial term in the third factor. That corresponds to having how many 3's, right? Because everything is a power multiple of 3. So if I take an x6, that would mean 2 3's, right? Because 2 3's will give me a total area of 2, or total content size of 2, of 6. So this thing corresponds to a 3. This thing that you said, 1 x squared from here and an x from here, that corresponds to a 2 and a 1. And this x cubed from here corresponds to 3 1, and so on. That's the proof. I mean, you just have to write out all the details, but this is the idea. Okay? This is really beautiful. So it required someone of his genius to realize this. Once you see it, I mean, the proof is not hard, but the hard part is coming up with the proof. Okay, so a teaser for tomorrow's, I'll stop with that. Oh, maybe actually we did start 5 minutes late, so I think I'm on time. So I'll explain one other result. I mean, we'll talk about many more results about partitions, but I want to illustrate one result that we will talk about next time. So we say that a partition is odd. I'll define it all next time. I'm just giving you a teaser. We say that a partition is odd if all its parts are odd, if it is only built up of odd integers. Okay? So how many odd partitions, what are the odd partitions of 6 that you see here? 5 1, 3 3, 1 1 1, 1 1 1 1. So how many odd partitions are there of 6? 4. we say that a partition is distinct if all its parts are different or are distinct. Okay? There should be no repetitions. How many distinct partitions of 6 do you see? Only one. How many? Well, okay, tell me, what are they? 6, 5, 1, 3, 2, 1. 4? So 4. So number of odd partitions of 6 and the number of distinct partitions of 6 are equal to 4. Okay? Again, Euler observed the beautiful theorem that this is true for all n, and I will prove this next time. Okay? And among many other nice results about partition. Okay, thank you. So if you want to know more about partitions, there's this very nice book called The Theory of Partitions by George Andrews. It's a Cambridge Mathematical Press volume. It has lots of nice problems and results.
Okay, thank you.